In this lecture, we'll talk about difference in difference estimators. The difference in difference technique allows you to gather information on the economic costs and benefits of a decision. And the name difference in difference, or diff in diff as it's sometimes called, comes from the fact that it involves two differences or subtraction problems. The first difference comes from measuring the effect or economic effect before versus after a decision or event. And the second difference comes from measuring the impact economically on two different groups. A treatment group or experimental group that receives some kind of new methodology or to which something is done, and a control or a placebo group that receives no change. To gather information about the benefits and costs of an economic decision, one way to do that is to run or design a natural experiment. What do we mean by a natural experiment? Let's take this example of a national restaurant chain. They had a regional manager in the Dallas-Fort Worth area who wanted to experiment with a new holiday menu and wanted to measure the profitability of introducing this new menu. So to do this, a new menu was introduced in half the restaurants in the Dallas area, but not in the Fort Worth area. So the Dallas group was the treatment or experimental group because they received the new menu. The Fort Worth restaurants represented the control group. The idea was that most of the economic forces affecting the restaurants in Dallas would also be present in Fort Worth, and so the one difference between these two restaurants during this holiday season was the introduction of the holiday menu. So by comparing sales at each group of restaurants before and after the holiday season, the regional manager calculated the first difference and found actually that the sales revenue went up. But the second difference comes from comparing the change in the Dallas restaurants to the change in the Fort Worth restaurants. And what the regional sales manager found was the difference between the two groups was essentially zero. Both groups experienced the same level of revenue increase. And the manager concluded from this that it wasn't in fact the experimental holiday menu that led to the revenue increase. Most likely, those menu items simply cannibalized sales from other items on the regular menu. The difference in difference estimator then uses before versus after the menu as the first difference, and then uses the Fort Worth group relative to the Dallas group as the difference between the experimental and the control. The Dallas group was actually the experimental group, the Fort Worth was the control group, but that represents the second difference in the analysis. So even though the restaurant sales increased, they increased equally at both restaurants. And this was seen in both the control and experimental group. And the economic logic or conclusion, therefore, is that the holiday menu didn't actually lead to or produce the observed increase in the Dallas revenue, or the Dallas restaurants' revenue. We can conclude this because we observed the same revenue increase in the control group, which did not receive the holiday menu. So the difference in difference technique is very simple, it's very powerful, and firms very often will engage proactively in changes in price or changes in product design and measure the differences. And those changes in product design or price will be implemented in only a select handful or subset of stores, thereby ensuring both a control and an experimental group. Natural experiments can be useful in many different economic contexts. For instance, in 1998, the Federal Trade Commission was looking at a merger in the Louisville, Kentucky area, a gasoline merger. And they used their own difference of, or their own version of the difference in difference estimator. They made a slight change or difference to the diff in diff estimator. And what they did was they looked at three control cities: Houston, Chicago, and Arlington, Virginia. And they used these to control for changes in supply and demand across different cities. The first difference that they calculated was that they looked at before versus after gas merger prices in Louisville, Kentucky, where they were concerned that a merger would actually lead to higher prices because of the concentration of power and ownership in the gasoline assets. So they were interested in asking, did this merger, was it anti-competitive? Did prices go up? So they looked at before versus after, and then they did the same thing in Chicago, in Arlington, and in Houston. Okay, so they've got before versus after, a difference for each city. Then they compared those differences across cities. And so for each of the three control cities, Houston, Arlington, and Chicago, they subtracted their pre-minus post difference from the Louisville pre-minus post difference. So they calculated really three diff-in-diff estimators, comparing Louisville separately to three different control cities. And when they did this, they found that actually the differences were essentially zero. From that, they concluded, by way of this diff-in-diff estimator, that the merger in Louisville did not seem to be anti-competitive, at least to the extent that it did not increase gas prices over and above what they were in other cities anyway, pre versus post merger. So it's a very interesting and a very useful tool, very simple to use, and it can be modified in almost any number of different contexts. Sometimes when we're faced with a decision, instead of focusing on, say, maximizing expected profits, benefits minus costs, we may want to minimize the expected error costs. Let's take the issue of global warming or climate change. If global warming is, say, caused by human activity, then a carbon tax, which would reduce the level of carbon consumption, might help mitigate the problem. On the other hand, if a carbon tax would be of little benefit if climate change is not produced by carbon and might have a negative economic impact. Well, there's still some, uncertainty about either is climate change caused by carbon, or more to the point, even if we agree upon that, to what extent is climate change linked to carbon, and how do we actually quantify and pin down the exact numerical relationship between the two? That's a very, very tricky problem, and there are a wide range of estimates on the exact relationship between the two. In other words, there's uncertainty. If we think about the kinds of errors we can make in economic decision making, we'll dichotomize those as type 1 and type 2 errors. A type 1 error in this case would be a failure to impose a tax when in fact carbon was resulting in climate change. In other words, it was caused by human activity. The other kind of error, a type 2 error, would be imposing the tax and later finding out that climate change was unrelated to human activity. Let's look at this in a 2x2 context here. We can see on the left side of this table, we've got global warming either is caused by human activity with a certain probability or is not with this other certain probability. Now, obviously, either it is or it isn't, but we don't know with certainty which one it is. So we're going to quantify our degree of uncertainty with regards to these two options by assigning P and 1 minus P. And of course, if you're certain, then you would just simply put 100% for the probability you were certain about. So this also accounts for or can be extended to that situation. If we impose a carbon tax and global warming is caused by human activity, the cost of making the wrong decision is zero. We made the right decision. And if it's not caused by human activity and we don't impose a tax, also we've made the right decision. The cost due to a wrong decision there is zero. We've made the right decision. But the two diagonal cells here quantify the economic cost of making the wrong decision. And they take the probability that we're wrong in that regard times the estimated error cost. Obviously, a key input in this number or in this analysis is how big economically are the errors going to be in either of the two situations. But even this type of simple analysis can help us begin to visualize and quantify the economic magnitude of different options and different types of decision errors when we're dealing with economic costs and uncertainty. The optimal decision in this context would be to choose the one with the smaller expected error costs. In other words, impose a carbon tax if the probability weighted cost of being wrong, should we do that, is less than the probability weighted cost of erring in the other direction. This type of analysis is especially useful when we're dealing with pricing problems, especially with assets with fixed capacity. Things like a stadium, a parking lot, an airline, a cruise ship, where the capacity is fixed. If demand turns out to be high, then underpricing is a mistake. If demand turns out to be relatively low, overpricing can be very costly because you have a lot of vacant seats or rooms or space in your parking lot. So dealing with fixed capacity asset pricing questions, very often, economists find this type of decision-making analysis to be very useful. Looking at the error costs. What if we price too high? What's the consequence? What if we price too low? What's the consequence there? And it's especially useful because with fixed assets, the errors are not symmetric. Very often the case of going wrong in one direction is kind of a minor error, and going wrong the other direction is quite a major error. And so by analyzing the magnitude of those errors and the probabilities that they can occur, this type of decision making lends itself very well to pricing decisions when dealing with assets with fixed capacity. In this lecture, we've talked about the diff-in-diff estimator and how to incorporate the probability of making certain types of errors and focusing in on minimizing expected error costs as opposed to maximizing expected profits. Thanks for listening.